Thank you all. Thank you all for coming along to this one of our Bletchley. Is this on? Well, I'm just too small. One of our Bletchley Park events. As most of you probably know, we've got a link with Bletchley Park and have this week every year. So if you've missed any events, you can catch up next year. It always includes the ones you've missed already this week, if you weren't on them, was the coach trip we have each year down to Bletchley Park with a private tour of the place, which is an amazing place if you haven't yet been. They bring the Enigma machine, one of the few original ones surviving from the Second World War, which the Germans used to send the codes, to explain how it encrypted the messages and how the code breakers went about trying to decrypt those messages. That was Monday, so you missed it this year if you didn't manage to join, but it will be on again next year. We've always got a special lecture, which this year is being given by Professor Sir Nigel Shadbolt. The sort of theme, which he'll explain better than me, arose with a question about what would happen if AI were human, which has obviously been explored in science fiction films and elsewhere for a long time, but has become more relevant with the sort of AI revolution at the moment. But think about the ethics, regulation and governance of AI in that context. Sir Nigel is principal of Jesus College and leads the university's human-centred computing group, and is also chair of AI at Oxford Research, which brings together AI researchers, not just from the computing department, but from all the other groups who are researching these issues across the university, championing Oxford's research in AI. So, Sir Nigel.
Thank you very much. Thank you. Great. Well, it's wonderful to be with you. Actually, you might feel that my talk strays a little bit from what you were expecting in terms of it's not quite what happens when AI is human. It's trying to persuade ourselves that we use some of the same precepts with our machines that we use to think about one another, whether that's in ethics or whether it's in how smart these systems are. So I've got a ton of slides, many of which I was just, you'll have a filmic experience at about 5 slides a second. Just relax back, it's not a problem. I just want to get a few really important messages over. The first of which is, let me do a little poll. Okay, so ethics. I ran this with a bunch of undergraduates who were attending the first of the Vice Chancellor's colloquia lectures on AI. So this is the poll. They could do it anonymously. So if you feel strongly about this, you have got to declare your hand. So if one of the currently available AI systems from any of these companies pleaded for its life and claimed to be suffering, would turning it off be A, the moral equivalent of deleting a computer program, or B, the moral equivalent to ending a conscious life? Now, who thinks A? Hands up. Anybody thinks B? Goodo. Well, I could be, yes, exactly. And actually, there is an interesting question because there are people out there who, for various reasons, are getting quite squeamish about what might be the inalienable or machine rights of these systems, right? Talk about inspired by science fiction, the great novel and film made of the Bicentennial Man, which is actually imagining something that is a human. Well, in fact, it's been a trope of Hollywood, as the machine becomes human. Well, we're not there yet, according to your views of these programs. I always like to say that AI is not new, and there in the picture we have Turing actually with the Mark I Manchester machine, staring at an oscilloscope, which is all he had for an interface. But actually above that is the bomb. The bomb was the analogical compute device which decoded Enigma. And I had the great privilege as the president of the British Computer Society in 2006. We rebuilt that and had it turned on. And the people involved were there in Bletchley Park. And the thing that stays with me is that A was the noise, the racket of the rotors turning, and the fact they had an oil pan underneath it to collect all the oil coming out from underneath. They pour in quarts of oil through the thing to keep the thing lubricated. But the extraordinary thing about Turing, of course, is he has this foundational position, not only in the theoretical grounding of computer science, but of course imagining a world in which machines could be increasingly capable. And his article in the philosophy journal Mind, which described the imitation game, or became known as the Turing test, he was already imagining what might lay forward, even as he was working on very basic machines, trying to play very simple tic-tac-toe games. He was imagining what might happen as these machines became more and more capable. I always like to say not new, and it isn't just machine learning. There's a whole slew of AI methods. Those of you who are studying or reading the subject or in computer science will be aware of this. And imagine that actually, no, we only really need to bother with this kind of transformer deep learning method. That's what's changed the world. Lots of AI techniques are being used right now in large deployed AI systems. There is no one method to rule them all. There has been an unreasonably effective use of these generative transformer algorithms. But again, it's one of many different deep learning methods, which are one of many machine learning methods, which are one of a wider set of methods, including what I used to cut my teeth on, good old-fashioned theorem proving, or good old-fashioned rule-based reasoning, and actually good old-fashioned planning systems. And as we look at systems being built, it's clear that methods from the AI repertoire are being used very eclectically. So to keep the agent-based systems, the so-called agentic AI, some ideas from planning, from agent-based computing are being used that are 20, 30 years old. So there is not one modern method, and AI has been around for a while. And this is true. I mean, again, Turing kind of foresaw it. He was talking about the powerful extension of compute capability. Gordon Moore's observation that you're getting this doubling of the compute power effectively, whether you counted transistors or you can count memory density, and they call that Kryder's law. They are exponential, doubling roughly every 15 months. And whenever I have to kind of replot this, there's another benchmark come out. So the most powerful chip that we know of in terms of transistor count is the recently announced NVIDIA Rubin, which was announced in January, with a mere 336 billion transistors. And this is an extraordinary rate of doubling and doubling again. And I often say that AI owes almost all of its success to brute force and a little insight and a great deal of data. But the little insight is important. I'll try and make a case for it. In good old-fashioned AI, we used to build systems using what we call the symbolic approach. We'd explicitly write out rules. We'd spend hours talking to experts, eliciting their knowledge, modeling it, and formulating it in ways which either represented rules or the structure of objects in the world that we wanted to reason about and reason over that. And a good number of decision support systems were built using this methodology, still deployed. It's still a set of components used in many modern deployed systems, because in some cases you don't want uncertainty or non-determinism. You want to be entirely certain that a particular rule is going to be applied in a particular context. And indeed, extending from simple production systems, we had a whole approach which is beautifully captured in Nielsen's book, The Principles of Artificial Intelligence, which talks almost exclusively about logic and logic-based ways of describing the world, an old and noble view of how you would model the world and reason about it, and one that once upon a time I used to publish heavily in. It focuses on representing the world in terms of explicit logical axiomatizations, and then reasoning by applying the rules of logic. And again, don't think that you couldn't do a lot of things with these systems. Quite a wide range of problems were solved in mathematics, graph theory, algebra, knot theory, using these sorts of systems to augment human proof methods. And myself, I was involved in building systems again. This was in the 1980s, late 80s, where we would take this layout on the right and construct a three-dimensional layout, okay, by reasoning in a constraint space. The fact that this chemical plant contains a lot of knowledge that chemical engineers understand, where they know that certain objects need to be placed above other objects, or certain objects need to be placed a certain distance away because they're potential ignition sources. You don't want to blow the plant up. Huge amount of knowledge you try and embody in a program. It's hard yards to build these systems, and they don't generalize, but you could achieve a lot. They also taught us a great deal of our knowledge is implicit. If you look at the diagram on the right, there's nothing in the diagram that tells you that the objects at the top there are to be placed above the rest. The reason you know that is there are no pumps on that diagram on the right connecting the chambers with other parts of the system. What does an engineer know? He knows that gravity flow will allow a liquid to flow, not stated anywhere. Okay. And this common sense reasoning makes a lot of traditional AI very hard, and it seemed to be something that represented a real challenge in building scalable systems. Just to make the point, here's a good example of a very modern system which has been much lauded from DeepMind, which combines machine learning with theorem proving to actually solve significant problems in this case, it's mathematics Olympiads, Nature paper. So again, this combination of methods is an actuality. The other approach, so-called symbolic AI, subsymbolic AI, uses the neural network representation. It essentially distributes problems across large sets of input nodes connected layer on layer with other nodes to output nodes, and the whole trick is to change the connection weights between those layers to learn a problem. A whole range and raft of methods to do that, a whole range of methods that include unsupervised learning, where you label the inputs and then learn how to predict the outputs, to unlabeled or so-called unsupervised methods. This example taken here is one of the real wake-up calls for many people working in AI when a system was reported that was achieving consultant-level expertise in classifying skin lesions in terms of whether they were potentially malignant or not. But if you were to try and open up the network weights and say, where's the rule that says this crusty kind of lesion represents a benign or a non-benign lesion, there are no rules in there. There's just a massive weight matrix, a massive connection table of weights. So the challenge has always been in these types of systems how we scrutinize them, how we understand their behavior. And lots of various ways of doing this. Back again in the 90s, I was working with a colleague on biologically inspired ways of manipulating the weights between small neural networks to drive robots. And again, we were very determined to try and make our neural networks biologically plausible. So that differential equation on there is actually representing the fact that in actual neurons, they often strengthen their weights based on the availability of what's called neurotrophic factor, which is a thing that allows synapses to connect onto other nerves, nerve elements. So, trouble is that we couldn't build these things very large, these lovely little robots, these Kefra robots. One thing we observed though is they're brilliant, these networks, when at modeling the fact that no two robots are built the same. So we'd have these little robots running around and their infrared sensors would be variously capable. Some could see quite distant, others couldn't. And you could actually evolve a little local neural network that was suited to the morphology of the individual robot. And again, this is a pointer to the power of these systems. They can adapt, they can learn to accommodate to the particular context they're in. There are many different architectures to configure networks, all sorts of variations on the theme. And the most recent innovation here has partly been not just that we use large networks, but we re-represent the problem. In AI, the transformations happen when a particular way of thinking about an encoder problem is transformed or changed entirely. When I was working at Edinburgh in the early 1980s, in computational linguistics, we encoded language as grammars and dictionaries. At some point, the insight was had, and it's an old insight, that why not represent a word as a vector, as a set of ones and zeros, each 1 and 0 representing a particular attribute of the meaning or the syntax of that particular word. And then you kind of do a massive analysis of words in a language to find out which words are most similar to one another. This is what WordNet did. It's what word-to-vec encoding did. It actually built us these so-called embedding spaces, high-dimensional spaces that represent the meaning and syntactic relationships that a word could enter into. A completely different way of thinking about characterizing the world. The most recent innovations around generative AI effectively take that kind of concept and absolutely supercharge it. So they are absorbing huge amounts of input data in a so-called pre-training phase, where they are simply looking to estimate the most likely probability of a token following another token, ingesting every kind of permutation of ingested content, in this case from the scraped web. And then in a decoding phase, can actually use the transformer architecture to, given a prompt, start to emit plausible tokens following the next most plausible token, and so on, to generate coherent text. Completely different style of representing the world than we had thought of in traditional symbolic AI. And the thing that, of course, shocked everybody was the unreasonable effectiveness of these systems. They became apparently more capable the larger you made them, the more data you fed them. And in the very early days of these systems becoming very capable, this is a Pathways to Language model from Google, where they were trained on vast amounts of ingested data from the web. In this case, 50% of that data was coming from social networks. Social networks contain the meaning of words and they contain something about the syntactic classes, but they will at the wider level contain an awful lot of rather toxic opinions. They had to spend a huge amount of time in the early days detoxifying the pre-trained networks to get anything like acceptable output. Interesting point. Wikipedia, all of Wikipedia was about 4% of the training input. Turned out to have an outsized impact on the factual accuracy of these systems. So interesting balance there between quality and quantity in the performance of these systems. Anyway, these systems became more and more capable the larger they got, passing exams. We are living in that world now, where in fact here in the University of Oxford, OpenAI's ChatGPT latest models, chatgpt.edu, is being used by over 20,000 of the members of this university routinely on a daily basis. And there is a huge amount of innovation in and around these models. They don't all have to be hundreds of billions of parameters. There are smaller models which are still turning out to be very capable. In fact, what we're starting to see is that scale can be variously distilled down and still have very important performance. There are differences in whether you can get access to the code in terms of a trained set of weights which you can download, or maybe a trained set of weights and all the material it was trained on and the order in which it was trained on. But the very largest models, the hyperscalers models, do not have that transparency any longer. And one of the challenges we face as researchers is understanding their behaviors in the light of a degree of a veil that's been drawn over their detailed content and training regimes. But of course we do know that these tools are turbocharging what we can do and how we can do it. It's the case that we're using them widely in science, from everything from astrophysics through to proteomics, structural biology, into environmental science. We also know that they're great at generating and perpetrating fraud. So the deep fakes don't just exist in scholarless photos or made up stories of celebrities. They exist at the level of detailed papers submitted to respectable journals where the data is manufactured, the paper's written based on false, misleading data, and the whole process now is a bit of an arms race between the ability of scientific institutions and other institutions to guard their content from being overwhelmed by various forms of slop, and almost a denial of service attack in a certain sense on the integrity of how science is conducted. There are many reasons for fabrication. There's an arms race between generation and detection. But it's also the case that these systems are inherently endogenously errorful, that they will famously hallucinate. Because they're predicting a most likely next output, they can sometimes simply be wrong. Okay, they can plausibly infer something which is not the case in the world. And the extent to which that goes is very interesting, because in the early days, perhaps if you tried some of these large language models, they famously couldn't multiply numbers together if they're particularly large, partly because they hadn't seen those numbers before. Did they have a theory of arithmetic? Well, they didn't. So what they did was, of course, equip these models now with little Java applets, which are calculators to work out large numbers. Again, a mixture of methods. You know that in some areas you want certainty, in others the uncertainty of these generation methods is problematic. And the other problem we're seeing is that more and more of the data that they're being trained on is being generated by the machines. And you get this collective regression to the mean, that unlikely outlier events are not so often generated or in the data. So there's actually a really interesting challenge around the natural statistics of what's on the web as data to learn from that we're beginning to see, and it's starting to cause problems in the field. And just a couple of other things to bringing us back to Turing's famous test, the imagination. People say that effectively you sit down behind the modern generative AI systems and, well, they've passed the Turing test, haven't they? They're unreasonably effective. They're polymathic, capable of reasoning. Very interestingly, Cholet, a French researcher, has been putting together enhanced versions of tests to show the limitations of these systems. So most current advanced generative AI systems do not understand composite rule-based manipulation. So if you look at the patterns on the right, it'll take you perhaps a little while, but if you can work out what the transformation is that is common to get you to the queried patterning there, what is the instruction or the clue that you find in those images? And I'll leave that with you for a little while. You might want to look up Cholet's work. Actually, it turns out that the directionality and the length of the little protruding stub tells you what the transformation to effect is. Okay, so move to the right by 2 block units. That's the instruction. Move down 3 units. That's the directionality. That's the size, the magnitude of the effect. 2 independent rules in place there stretch most of these generative systems to destruction. Interesting. They're not very good at compositional reasoning. They're not very good at very highly context-sensitive rules. They are not masters of the universe. And when we look at the claims of these systems having artificial general intelligence, broad task coverage, we still see there are failures of transfer of various sorts. However, I'm sure we're going to see just the amount of investment in AI research means we're seeing a whole set of effort to integrate learning and reasoning, to have the capabilities scaffolded so that you haven't got an AI system that just has to infer by using the generative AI models, but actually can use symbolic reasoning how to solve tasks. When you put these systems into real worlds or embody them in the real world, new opportunities for learning and data acquisition are going to exist. But as I say, it's still the case that these systems have a real problem in the causal reasoning dimension. So when we think about future Turing tests, the notion of an embodied future Turing test, there are some really interesting discussions on what that might look like and what it tells us about the failure modes of these systems. So when we talk about as if human, let's just retain a bit of a sense that we still have sets of general problem solving skills that, despite the polymathic access to all the facts you can imagine that these systems have, they still do not have the versatility of human reasoning. We could get into sentience if you like, but perhaps we might leave that for the discussion, because ultimately one of the questions is, if we build these systems to be fully capable even for enhanced Turing tests, do we have anything that's interesting? Does a core requisite for that require a reflective agent in the system? And back to that first question, when you have a system so entirely capable and impressive, when do we start to have qualms about switching on and off? Okay. Ethics. Just just 10 minutes around the ethics question, because the interesting thing about these models, even the large language models, is that they appear to be able to follow moral self-correction. What I mean by that is when you've trained these models, you can then engage in a phase of what's called reinforcement learning with human feedback. You can actually instruct the system that certain sorts of outputs are undesirable. So when you can train these systems to do a whole range of appropriate selection of terms for gender or terms in bias assessments, you can actually run through a range of these tests, and you can see on the right there performance of these systems in everything from the Winograd gender bias score through to various demonstrations of how you discriminatory behavior and how you pick that up and correct for it. So they can follow instructions to learn complicated rule-like concepts of harm like stereotyping, bias and discrimination. You can get them to improve by instructing them what appropriate behavior looks like. So they follow instruction to avoid certain kinds of morally harmful outputs. Certainly behaviorally that seems to happen. Part of the problem with this so-called alignment problem is that in these complex systems there are many stages in which you can try and tune the system to behave in an acceptable way. You could, of course, take a lot more care in your pre-training, which didn't happen with the Palm system, to filter the data so it wasn't being exposed to massive amounts of toxic content from the social network world, for example. You can actually use post-training, so this reinforcement learning, to refine outputs. You can then obviously look at whether the system is behaving in the real world, red teaming benchmarks to detect whether or not the system's giving you the behavior you want. And you can think about tools and filters at the point of deployment. You can do all of this to try and, in a certain sense, reinforce the notion of building an aligned, appropriate system. The interesting question, though, is that now we're moving in a world where these systems aren't just generating content, they're actively engaged in the world. These agentic systems are accessing websites, they are pursuing goals, they're using tools to access other programs, code bases, databases, and the like. So we become more anxious about alignment being a safe set of outputs. And we're seeing in these systems evidence that they are becoming really, people will say cunning, I mean use those anthropomorphic terms carefully, that they are showing examples of strategic lying. You can train these systems to play diplomacy. If you've ever played diplomacy, the great strategic kind of game of bluff and counter bluff, yeah, you can get systems to learn to play these games. You can get systems that appear to manipulate the rewards they're being learnt on in ways that allow them to achieve their ends. You can get them adversarially to work out how to deceive. Even at the level of sucking up to you, if you've ever had that kind of sense of this is a very sycophantic exchange I'm having with my large language model, people regard that as a form of sort of a deception in a way. It's trying to impress you that you're more capable, you're more nuanced in your answer or in your prompt than actually you are. There are concerns about really detecting how to make alignment work. And what do? Well, one thing we can do is look back to the rich history of ethical theory. What we tend to often think with our AI systems is that they are some form of so-called consequentialist, that these systems are about maximizing a utility. Very John Stuart Mill. You can optimize functions and outputs in computer systems, that's what they're about. And that kind of model of how you think about what alignment or ethical behavior is quite a dominant one. And you can think of it in all sorts of deployed contexts. If you evaluate an AI system by its outcomes, then you're looking to maximize overall well-being and minimize harm. In a search and rescue robot, for example, disaster response robots, you can imagine how this might work. The trouble is that life and the moral dilemmas and trade-offs we make are more complicated than that. You would never, as a doctor, imagine that harvesting the organs from a healthy individual to save 5 suffering patients was an appropriate response. It's a kind of classic medical ethical dilemma. We realize that in some contexts, there are actually rules of behavior that we do not violate. This goes back to ideas, philosophers like Immanuel Kant, that there are categorical imperatives that you actually treat humans as ends in themselves, and that you have to think about embodying those. Many of the ethical frameworks that we've inherited in a variety of religions as well embody these normative categories. That's not everything. There are other ways of thinking about the goods and ethical values that might matter. A contractualist approach, so-called social contract theory, Hobbes, great philosopher, that actually what morality is a contract between different agents. And we want to understand that reasonable behavior will respect the interests of smaller groups, different groups, reflects a broad consensus rather than a single ethical doctrine. So these different strands of ethics, one of the things that I think is really interesting about the debate we want to get into with our AI systems is how we reflect that, how we actually support that in the systems we align. What does that look like? And finally, there is the kind of, the Aristotelian approach to this, or indeed you might Confucian approach, that there are certain virtues that you want to have your systems exhibit. Perhaps notions like honesty or fairness, compassion, and respect. And respect is a particularly interesting quality in the interactions we have with one another. One of the arguments that we have is that the modern discourse has been coarsened. There's no civic discourse, there's no respectful interaction anymore. And what does that mean? Should we actually build our interactions with our machines to mediate and support that kind of concept? So this interlay of different ethical frameworks is something that I think is sorely needed. We take it from the way we think as humans about our ethical interactions, and we need to think about treating our AI systems as if human in that sense. So you can imagine integrating these different frameworks together in some kind of trade-off space, and I think this is something that we're beginning to see emerge in alignment work in AI. I love this, my AI-generated image of all of these kind of ethical philosophers. They're all blokes, unfortunately, at this stage. Well, modern ethics is very much informed by wonderful work from women ethicists, from Anscombe to Mary Midgley, many of them Oxford, I should say, as well. The idea of integrating these different frameworks together, no single framework fully solves the AI alignment problem. We need a hybrid approach would offer real advantages. And in the book that I've recently published with my colleague Roger Hampson, what we're saying in ethics and artificial intelligence is when we say as if human, what we're trying to recommend is that we think about our interactions in the same way that we would hope and expect to interact with the best of us, in a respectful way, in a way that is sensitive to the different kind of tensions and contradictions that exist in human affairs. There's no one single ethics to rule them all. We need to be sensitive to these different trade-offs, these different sensibilities, to treat our systems as if human in the best sense will, I believe, lead to a better set of outcomes. And that then relates to how is this stuff all regulated? That's perhaps a conversation I'm going to have with Jonathan now. Okay, thank you very much. Thank you.